Thank you to everyone who is watching this recording or has tuned in. Today we are here with Professor Scott Clark. My name is Hannah Bambra. I'm a provisional counsellor at the Mental Health Foundation of Australia, and I'll just be introducing Professor Scott Clark before we jump straight into today's topic. So Scott Clark is the discipline head for the University of Adelaide Discipline of Psychiatry. He coordinates the Adelaide Medical School's psychiatry program and is a consultant psychiatrist in the Western Community Mental Health Service. Scott's research focuses on novel clinical trials and the use of biomarkers and biotypes in the prediction of outcomes in serious mental illness. He is also on the board here at the Mental Health Foundation of Australia. And I'll hand over to Scott now to introduce today's topic.
Thanks, Hannah, and thanks for the Foundation for the opportunity to speak to a wider audience today. This topic with, I guess the emergence of AI and I guess, TikTok itself, the fact that we can now reliably extract speech and facial expression from video really is the tip of the iceberg in terms of the use of such technologies to help us as mental health practitioners work from day to day. And what I'm going to do today is take you through some of the studies that we've got in development here in Adelaide, and a little bit about the background, and try and convey sort of how significant a support this could be towards assessment and prediction and supporting longitudinal assessments of patients. Given that we've pivoted to a very much, a lot of our care is now delivered online post-COVID. So this could provide sort of an extra support mechanism to help in training clinicians, but also to make sure that we're collecting accurate information as we go and improving patient outcomes. So speech and facial features. So what sort of things, and I guess the science of collecting this sort of data was probably pioneered by TikTok, but there now are actually open source platforms, and we've coupled a number of them together that can actually extract this feature from high quality video. And I guess the quality of the video itself is important, the quality of the video and sound. And so the more higher resolution and the more detail that's captured, I guess the higher the accuracy of these metrics, and I'll talk a little bit more about that later. But we're talking here about facial movement, which is associated with expression of emotion. There is a science now around, an evolving science of classifying these facial movements. It's important to understand that there are significant cultural differences, and at the Mental Health Foundation, we're very aware of cross-cultural mental health and designing interventions and supporting people in culturally sensitive and appropriate ways. And I guess one of the limitations of the data collected so far is it's largely, of course, as most science is, unfortunately, in Caucasian populations. But we can collect facial expressions, and I guess these in response to interaction with a clinician, and these are changed significantly in disorders like major depression or even in psychosis, schizophrenia. Also head movements. And linguistic markers. So this is when we do assessments in psychiatry, we are assessing the form of the speech. So is the speech connected together to convey a message that indicates underlying thinking is organised? But also the content of the speech. So people are more preoccupied with certain topics. Someone who's depressed is preoccupied with negative features. Someone who has potentially a paranoid illness is more preoccupied with themes of threat from the environment. And they're incredibly complex metrics that we can now extract. And this also goes toward the sound that's made in speech. So the I guess the acoustic markers. And so this is a physical property of speech sound. So I've done a significant amount of work recently with engineering teams looking at the nature of speech. And that actually changes with changes in mood and also I guess in changes in thinking, and can be associated with physical illness, but also just mental illness in general. And I guess one of the fathers of phenomenology and psychiatric diagnosis, Kraepelin, first mentioned that speech characteristics in depressed patients, where patients speak in a low voice, slow, hesitatingly, monotonously, sometimes stuttering, whispering, try several times before they bring out a word, become mute in the middle of the sentence. With today's technology, we can describe these things in great detail and actually monitor the progress of those symptoms with treatment. So that's the power of being able to use these technologies now. And of course, as with all digital technologies and AI, there is the challenge of the security of data. And I guess the studies that we work with here at the university, we're able to extract these features and throw away the video data so that we can maintain patient confidentiality. But that's a large challenge, and I guess it's some of the concern that's expressed with platforms like TikTok that actually are maintaining this data. So if we first have a look at acoustic features, so there are factors that affect the sound that speech makes, and they include, I guess, the brain mechanisms of control and the thinking patterns, but also the motor patterns that are generated, and out through the brainstem and the spinal cord. And then there's the physical shape and the movement of the muscles and the space inside the pharynx and the nasal cavity that actually shapes the type of sound. And so features at the cognitive level, at the physiological level, can affect what comes out at the acoustic level. And I guess with changes in facial expression, your speech also changes. And I'm a part-time singer in another life. And so one of the things that I need to do to make sure that my notes are clear and on pitch is that use a smiling face, and that changes the nature of my voice as it comes out when I'm singing. So there's good evidence suggests that all of these things are dependent on things like mood and other illness. This is from a review paper that we wrote a couple of years back. Here again, I'm working with an engineering team. And so these features can be described in engineering terms. And so breaking it down into a model where there's a generator that creates a signal, and that signal goes through the upper respiratory tract and the pharynx and into the nasal cavities, and that acts as a filter. So the shape of the filter changes the sound, and also the nature of the generator. So the vocal cords, the muscles in, I guess, the diaphragm, and the pressure that's put behind the vocal cords, and all that needs to come together to make speech sounds. Is a highly complex process. And we can actually look at sound in terms of waves and frequencies and other engineering metrics to actually pull out these changes. And we can do that virtually in real time, just using complex mathematics that's embedded into some of these programs. And so the sort of acoustic features that we can pull out sort of include those related to the changes in the vocal folds, jitter and shimmer, so how much vibration there is. I mean, if there's hesitancy, anxiety in speech, there's more jitter and shimmer. There's the frequency, frequency of the content of speech, which is represented in clusters of different types of sounds. The prosody, the music-like aspects of speech, which is lost in psychosis and in severe major depression, where people's speech becomes flattened and monotonous. And the rhythm behind speech. And there's the resonance, which is expressed in the formants, and that speaks to the shape of the facial muscles and how that area is controlled during speech. And you can actually analyze all of these with an open source available toolbox. And this is one of the tools that we've assembled together to be able to assess and extract this data. And so if we look at the sort of studies that have used speech acoustics and in terms of depression and other features, and we can see that the pitch is often decreased in depression. but it's increased in anxiety disorders. So people's voice gets more high-pitched as they get more anxious, but it's more monotone and monotonous when people are depressed. Jitter, so period-to-period fluctuations in pitch. The precision of motor control is increased in depression, so there's a bit more of a muffled voice. And shimmer is increased in anxiety disorders. So this is again the precision of motor control. There's more vibration and more overcorrection. The speech rate is decreased in schizophrenia, where there's more poverty of thought. There are less thoughts happening, and so less speech comes out, and that includes the complexity of the nature of speech, and there are other metrics that sit inside that. And the mean duration of pauses, so that's increased both in psychosis because of the gaps in thinking, and also in bipolar disorder, and potentially in the depressive features of bipolar disorder, where people are struggling to get their ideas out because of the level of depression that they're suffering. So linguistic features, and this is the structure of speech in terms of how it hangs together in normal sentence structures, and how coherent it is. And I guess as clinicians, when we're assessing someone with a psychotic illness, then we're looking for thought disorder or tangentiality in thinking. And so we can pick that up in the structure. And I guess there's software now that can analyze the nature of the words in the speech and can pick up certain themes and but also extract those themes and look at if those themes are coherent within a piece of speech to see if there is tangentiality. And so there are these automatic natural language packages now. And there's a process called semantic latent analysis, which can plot different words and based on their relatedness. So again, highly sort of complex linguistic features that in the past would have required experts are now automated. So, how similar are the words in the text? And you can analyze that in individual speech virtually in real time. So in terms of the linguistic markers, we can see that the semantic similarity between words is decreased. The coherence is decreased in schizophrenia because of that thought disorder, and it's associated with tangentiality or derailment or circumstantiality. So not complete description of the ideas, the logical thinking and poverty of content, the coherence. The sentiment, so the emotional state of the person. So the type of words that are being used, the polarity of those words. So there's increased negative sentiment and depression. Cohesion, so the use of features, the way that language is structured, so the correct use of semantics and language structures is decreased in schizophrenia again because of that underlying thought disorder, which is reflected in speech. I guess the complexity and the use of pronouns and other contents of speech can be changed in things like post-traumatic stress disorder and also in schizophrenia as well. So again, here we're able to extract these complex linguistic features that would have taken people hours, days, and weeks to extract from recorded interviews previously. We're now able to automatically extract these sort of features. Okay. And here's particular linguistic features. Again, this is a study of psychosis and sort of higher level interesting features that have been associated with psychosis onset. So the coherence again with latent semantic analysis, the complexity of the speech, reduced complexity predicts psychosis onset. Poverty of content again predicts psychosis onset. Referential, so this refers to how people refer to the world internally and externally outside of them. And people at high risk, so CHR, clinical high risk of psychosis, show different types of coherence to healthy controls. Different use of metaphors and the corrective language correctiveness, so they're quite how well people are using the rules of language. And mania generally involves less thought disorder than schizophrenia, unless it's florid. But there's a difference there that can be used in diagnostic processes. So these linguistic features are really significant in terms of they exist across disorders. And one of the problems we have with psychiatric diagnosis these days is clustering in these groups where there are overlapping symptom domains, and there are transdiagnostic features. So, and one of those features that we research locally is disorder in sense of self. And I guess that expresses in dissociative disorders, but it happens in schizophrenia, and it's kind of been left out of the diagnostic criteria for schizophrenia in the Diagnostic and Statistical Manual. It's come to the forefront through Barnaby Nelson and others recently, and this study is a really good example of how people have similar symptoms across different disorders. And these transdiagnostic symptoms might represent a way forward to personalising care, because if you develop a treatment for a certain a transdiagnostic feature, then you're going to be able to use this across people to personalise the experience on top of anything that you might use for their individual diagnostic group. And so self-disorder, here we can see that using extracting features of linguistic features from a multi-disorder cohort. So we've got affective disorders, anxiety, developmental, attention deficit disorder. And we can see there are some common features. So in terms of self-disorder, in terms of prominent words about distorted terms of self, irregular use of language, about detachment and relationship between self and the world, changes in the way people describe their experience and how secure or ambivalent they are about the world around them and about their experience, changes in the use of pronouns, and unusual use of adjectives. And these have all been associated with this disorder of self that we can identify across disorders. And in future, we might be able to target, and we've done that in local clinics where in local early psychosis clinics, where one of the persons, there are a couple of cases we're writing up for a book now, but one striking case is where the person resonated so much with our identification using scales of this self-disorder that it became a central part of their therapy. The person felt more understood, they were able to engage more in care, and they developed some sort of cognitive behavioral approaches around this self-disorder, which resulted in a really good outcome. So it can help us personalize therapy in the future, I think. And these transdiagnostic features, which we couldn't really analyze before because they're kind of missing from the diagnostic criteria. So we're really generating probably a new phenomenology. And I guess, in 20 years' time, 10 years' time, who knows how fast things are moving these days, we might be more focused on these transdiagnostic features rather than trying to fit someone, fit a round peg into a square hole or a square peg into a round hole in terms of making people fit a specific diagnosis. And I think this is very powerful, and we'll wait and see how this evolves. So if we move on to facial features now, I guess the analysis of facial features, the science around it has developed from manual analysis and comparison of kind of known emotional expressions to this quite detailed set of criteria, looking purely at which parts of the face move at different times. So dividing the face up into regions and really looking individually at how those regions move. And I guess there is now concordance between automated analysis of these features and manual analysis using video, such that there's a concordance of about 0.73. So with high quality video, we can now reliably extract facial expressions. Now, there are emotion models that can underlie this, but again, I would suggest here that we need to be careful about different emotional expressions between genders and also between different cultures. And it may be really that with some of these specific digital markers, they are markers for an individual set of expressions, and we can see those change with treatment and hopefully in a positive direction. But it may be there's a lot of variance between people, so we're not necessarily trying to find the perfect facial expression or the perfect speech expression. But some of the features can convey features of depression or psychosis or distress. And we can track those over time, because if you've got video to compare to the previous session, then you might see the changes. And I mean, as clinicians, we stand back and we interact with patients and we get a sense of how they're feeling and how things have changed. For junior clinicians, they might miss things in the conversation. I guess the other power of this sort of technology can be used in day-to-day interactions. Again, becomes more invasive and intrusive, but you could have these running in the background with interactions, during a clinic, or using your video phone during the day and picking up these subtle cues and feeding it back to the individual patient that they're improving or that things are not going so well. I mean, ultimately, people know how they're feeling on the day, so it's not to it's not replacing that, but it adds. I guess we might be practicing in some sort of augmented type of reality at some point in the future. Just bear with me. I've just got a pop-up that I need to close. So I can get back to the presentation. Thank you. So here, Charles Darwin commented about when low in spirits, the corners of the mouth are depressed, the inner corner of the eyebrows are raised by the muscle, which the French call the grief muscle of the eyebrow. And this state becomes slightly oblique with a little swelling at the inner end. And the forehead is transversely wrinkled in the middle part. We can objectively measure these things. We just got a review in submission of some of these studies, which I'll step through now. And so what can we measure with these facial features? We can look at the mean number of blinks, and actually blinking is associated with central dopamine tone, which might be increased in schizophrenia, but it's also decreased in Parkinson's. So some of these measures would obviously be helpful in neurological conditions as well. So the direction of a person's gaze in another person's eyes, and we can actually, the package we've got can actually extract video from both the interviewer and the interviewee online, and we can compare those and look at how they're associated. But I guess in schizophrenia and social anxiety, and probably also in autism spectrum disorders, there would be some sort of gaze aversion or differences in gaze. Facial muscles. So some of, historically, this has been measured by using EMG, so measuring the electrical activity of muscles on the face, or by sort of reviewing video. The automated processes are really new over the last few years. So here are some studies where the facial expression and certain features of facial expression, Carney et al. Was associated with subsequent improvement. So good responders, also the study by Gren et al., where good responders had specific EMG activity in the zygomatic muscle. Obviously, these studies augment stuff that we can see in individuals face to face, and clinicians may ask, what is the use of this? But again, it provides some feedback and it provides some objective measurements over time that could be used to train people. And I guess in terms of their clinical abilities, can they identify these things? But also, it provides a distinct record of how someone is changing and improving over time. And the latest software, which we've combined with OpenSmile, is OpenFace. And there's the bottom study there was using an underlying emotional model. And remember, I said there are some limitations to those emotional models because they are, developed in Caucasian populations, and we need to be careful about cross-cultural interpretation. So we could see here that the intensity of emotions reduced with response to antidepressant treatment, as measured with the MADRS, which is a standard depression scale. So we can capture these subtle components in real time, and we might be able to have our own little AI working alongside us as clinicians that is just reminding us that we might have missed something, or that is pointing out these transdiagnostic symptoms. So we might have missed this self-disorder that was described by the patient in terms of it's not part of the things that we normally collect, but an augmented clinical assistant might be able to remind us of those things and help us in subsequent assessment. Okay. So, are we looking at a digital future? So how can we, can we combine the power of these linguistic markers, these acoustic markers, and understand facial movement, and then embed that in clinical care and in medical education, in ambulatory care? So is there some sort of ecosystem where we provide training and feedback on clinical skills using AI. We've and using these detailed facial biomarkers. So currently we're implementing a trial of virtual reality social cognitive therapy in psychosis. This is a VISA trial led by Andy Thompson from Origin. And in those in the virtual AI training, people are able to get involved in social situations and test out their abilities and understand their associated anxiety. But they can replay the social interaction because they're working in a virtual world using avatars. And so that's kind of very powerful that people can come back and practice those situations. But we might also be able to give them feedback on how they're speaking and how they're interacting at the same time. And train clinicians, but also train patients to in forms of therapy that better interact. In terms of clinical care, as I said, it'll pick up these subtle cues and augment information that we're collecting in face-to-face interviews. And we can then track these symptoms longitudinally. And it might be that one day the clinical trials are run based on these objective measures of improvement with intervention with treatments. But, as clinicians, if we had a good record and we can share with the patients, obviously these AI-based assistants need to be, local data needs to be collected and presented and not shared in terms of, we need to be careful about the issues of ethics and data security, but you can implement these models locally. But, an individual might even own their own AI representation themselves, and they can track their own process through care. Just like we have, I guess, the shared digital health record these days. Maybe we can have an AI version of ourselves that captures these symptoms. In ambulatory care, so can we use this sort of technology to capture snapshots in day-to-day activities? So, when we're interacting with someone on the phone, as I said, that can be summarized and then presented to the clinician the next time you come in, and you can have a discussion about how you might have been improving or things might have been going backwards based on the therapy. We kind of do that now with Holter monitoring in cardiology. So if someone's having an arrhythmia that is intermittent and it's hard for the clinician to actually be there to analyze that data, you get a Holter monitor, and that collects data 24/7 for a month. Or you can trigger it when there are specific events. And then you can come back and review that data with the specialist, or it might even go directly to the specialist and they can review that data as they go, as they're available. And so it might be very powerful to be able to capture some of this data with the caveats of obviously data security and safety. So it's a brave new world in terms of what the possibilities are. So this brings us to the system that we've been able to put together locally and gluing together some of these open source platforms under the DigBio platform, which Simon Hartman here has postdoc engineer whose attention to detail and amazing skill set has been able to glue all these things together. And so we're able to de-identify features as we go. We use upload video files and extract, I guess, open smile, speech, open face, facial movement, and OpenAI Whisper to extract all of the digital features of the content of the language. And you can develop transcriptions, and we can delete the videos to protect people's identity. And we use a secure HIPAA platform to be able to collect this data so that, to prevent any hacking in the process. Automatically separates audio and video streams. We do have streams for both the interviewer and the participant. So automatic transcription using large language models. So we extract the speech using OpenAI, and then we can use that speech to analyze the metrics in terms of speech content that I was talking about previously, and I'll show you some examples in a minute. And I guess different size models, and OpenAI is evolving all the time, and that technology will continue to evolve. But what we're able to do is, to modify that as we go and increase the accuracy which speech features can be extracted. This is the sort of output from the model, so we can see linguistics features that are significant from current studies, and you would have seen some of those presented previously, like the length of sentences, the sentiment, the similarity in terms of the coherence of the speech, word counts, so the use of different types of language, the interaction between the patient and the participant. In terms of the speech acoustics, this is very rich data, and there are significantly more variables there, but we can see how different characteristics of the speech changes over time. And the facial features, we collect all of the data on from that, I guess the international standard for facial movements, and then we're able to look at patterns and look at patterns over time. So, we really are now starting to collect this data in studies, and I'll give you an example in a second. So, this is the interface using OpenFace. I haven't got a video that I can run now, but in real time, you can see on the right-hand side there are the bars which are different colours, and the activation across those bars changes systematically with movement in the face and movement with the head. And so that actually operates in real time. And you can see the diagram down here where tilting and shifting is reflected in those metrics. And you can put facial kind of emotional recognition models on the back of that, or you can look at that data individually. And I think we're advocating for the moment just to look at individual differences rather than enforcing an emotional model which may not suit the person. But there are studies that have used these emotional models. So here's how exciting this gets. So we're currently looking at and doing this on an international basis. So looking at how brainwaves, so working with Circa and the Uni of Nottingham to measure brainwaves in Nottingham while we're extracting video features in Adelaide in Australia. And we're not quite doing this in real time yet, but we're able to record the video here using HIPAA and use this new quantum MEG technology, which it gives incredibly rich data on deep magnetic fluctuations associated with brain activity. The data is so rich, we're just working on pilot data and picking through and trying to work out some metrics at the moment that we can use to associate with facial expression. And the plan is in the coming months to start a study of depressed individuals and look at how the different brain networks are contributing to speech production and facial expression within disorders. And the idea being that we can develop further biomarkers with larger samples to help understand the changes in neural mechanisms and potentially to understand some of these cross-diagnostic, trans-diagnostic features that might be informative of new ways of care. And we're looking at a rich study in how diet affects cognition and mood. So it becomes incredibly complex, but these things are incredibly powerful. We can actually get down to looking at the EEG state of the brain in the context of specific words. So we can actually identify words and phrases and facial expressions, and then look at what the brain's doing during individual components. And these become like event-related potentials. So ERPs are used in brain science. They're usually simple paradigms where you respond to a sound or or some visual stimulus. But we can develop these complex paradigms now using this science, which is really incredibly exciting moving forward. So there are some key studies that we're involved in, large-scale studies where this sort of data is being collected, and the Accelerating Medicines Partnership AMP Schizophrenia is an NIMH-funded study. Large networks here led by Origin, where we're I'm one of the local PIs in Australia. International network, about 3,000 participants, a large group based in the US, large group based from Australia, but there's international reach into Asia and South America and Europe as well. And so they are collecting data using OpenFace and OpenSmile. I guess these are some early analyses. What we're trying to develop is a science around these metrics. And we have a couple of data point collections, and we're looking at the reliability of these measures in patients that are followed up. So these are patients with ultra high risk of having a psychotic episode. So the clinical high risk is the basis of early intervention. Authors like Pat McGorry and Barnaby Nelson, who's one of the lead PIs here, developing a science of knowing when people are getting closer to a psychotic episode, so that we can intervene effectively and prevent the onset of that first psychotic episode, which is incredibly distressing and disruptive, and managing people to try and prevent those episodes might actually reduce some of the damage caused by those experiences. And we can see here that we've got a couple of samples in terms of, we've got a sample comparing baseline and a point at 2 months follow-up. And the repeatability of these measures between sort of 0.4 and 0.5 down here. Some measures are more repeatable than others, but it shows that they're a reasonable metric. So we're defining the engineering of these features so that we can use them more effectively in the future. And so that's it's an incredible project to be a part of. And Simon Hartman again is doing some of these analyses so that we can better understand the reliability of this data and develop trust in these metrics that clinicians can use them in the future. Here's some studies we did with a local engineering team looking at available data, and we can see what this shows is that the number of reproducible bioacoustic features actually changes for females and males. So some features are more or less reliable in males and females, and we need to consider that in the way we implement those packages across gender. And part of the same study, here we can see that across different tasks, some of these different metrics have different accuracies. And so if we compare counting versus reading a story, this is a collected, publicly available data set, different metrics are more accurate for different components. So it may be that we need to develop a sort of an automated, flexible model that uses the right metrics given the speech that's in front of us at any given time. So that's also, this is fundamental basic science work that needs to be done to build up, a true science of using these digital markers. And, at some point in the future, here's a paper by Zaya and others, and Lena Paliapian, who's one of the leaders in some of this digital technology, where, we can look at the content of person's interaction with social media, We can intervene and talk to people on the phone and collect speech data. We can use potentially geolocations actually used in schizophrenia with permission, of course. Again, we need to be careful about how intrusive this is, but some of that information can be extracted into just how much movement there is if you're staying at home all the time or if you're going out, not exactly where you are so that you're not identified. We can look at speech acoustics, how it evolves over time. We can look at how speech might change in phone calls or in clinical interactions, and we can build networks, and we can use that, give patients access to their own data and for lived experience to kind of understand a little bit like how we now use iPhones collecting all of our physical health data, and how many steps have you done today. It might be feeding back some of this information to know what your state of mind is. You might use mindfulness meditation to help improve your state of mind on a given day based on some of these features. Also do some work with Insight Timer around developing a science of how meditation and other features could help in these situations. So again, it's incredibly exciting, but quite scary in terms of the level of data that might be able to be extracted. It needs to be permissioned, it needs to be secure, and it needs to be kind of led by lived experience and people wanting to engage. In conclusion, what we can see is that AI is rapidly progressing, and I guess businesses like TikTok may well be collecting and extracting and processing these features with your permission when you click yes to engage in the platform. So the science is evolving around us. There's really work to do around reliability and gender and cultural differences to make sure that that there's talk about sort of cultural bias in AI in general on the internet, and really then we need to be very careful that we don't exclude or over-include people in certain groups based on individual differences, and maybe there should be a science around a person owning their individual differences and then being able to work with clinicians about that rather than having models enforced top down onto people. An AI interview assistant is a distinct possibility in coming years as this science develops. But we need large-scale data to refine systems, and we need to and it's a distinct possibility for expanded phenomenology. So we can use these transdiagnostic features to better understand the science of mental health resilience and mental illness. And we may be able to better understand psychopathology and linking to EEG, magnetoencephalography, the measuring of brainwaves, the measuring of other physiology, the understanding of genomics, to better understand the nature of psychopathology by linking data to some of these tools. And these tools, it's early days, but can be used to track a patient's journey and predict risk and to inform the patient. Again, here, I think it's important that this is patient-led and it's not top-down enforced, and people own their data and their journey. So that's my presentation for today. I'm happy to take any questions.
We might just give people a second to pop questions in the chat by using the Q&A function that should be at the bottom of their screen if they want to. I did have a question to kick things off.
Yeah.
You sort of touched on at the end sort of issues that might come up around privacy and security and that kind of thing. How could counsellors or anyone in healthcare kind of use this technology in a way that respects people's right to privacy and that kind of thing? How could they approach those conversations at the start of a session is something I was interested in.
Well, I think you need to provide some reassurance about how the data is being used. There needs to be rigorous local management of that data. So AI instances, so we're implementing these algorithms, and data is stored with consent on university databases and then de-identified. So if you were working with someone in a clinic, that clinic needs to be, the patient needs to be sure that that data stays on site and that it's well protected. There's, I guess, the challenge is there is no guarantees these days, but the internet and people on it are collecting data about us all the time. It does, it does pose some risks, but these need to be rigorously dealt with. And I guess, as part of signing on to therapy, there needs to be some permission about whether you use AI or not, and that needs to be informed consent, really. So the person needs to understand what security that you have on site and how that will protect them from potential data leakage.
That makes sense. And one more question. Sorry, it was a very interesting presentation. Is there any implications, or is there any studies and research that have been done with people who are living with disabilities and how that might impact their facial expressions?
Well, no, I mean, there's actually a lot of work, and I was talking to a colleague the other day about, and we've actually got a grant in implementing this in stroke patients, because I think this is powerful biofeedback, and I think you could actually leverage that to help people recover from strokes. I mean, it's obviously very confronting for individuals who have lost capacity and have some disability, but also it might be empowering and allow them to take control. And so that needs to be handled very carefully, with individuals. But I might stop sharing if that's. Um, but it could be quite liberating and powerful. I mean, again, these technologies should work for us and not against us, and we should set them up with lived experience. We co-design, so we design apps. We're working on an app with the local Arabic community, but it needs to be authentic in terms of have lived experience input and designed in a way that is acceptable to people that that have some sort of disability, but also it needs to be designed to enhance their functional capacity. And biofeedback is very powerful for that.
That's great. Thank you, Scott. We don't have any more questions in the chat at this stage. I think you had a very thorough presentation, but your last topic that you touched on was a very empowering note to end on. So thank you so much for everything that you've shared today and for joining the Wellness Hub, Scott.
No problems. Always happy to support the great work of the Mental Health Foundation of Australia, and look forward to working with you in the future. Thank you.